Hello everybody. Today I'm going to explain the solution for the third problem of the week, which is a problem chosen by the people from the Discord server. The link is in the description if you want to join it. And the problem was chosen from the AtCoder Regular Contest 107. And the problem is the number of multisets. And in this task, we are given two positive integers n and k. And we need to find the number of multisets which have n elements and the sum is equal to k. And each element of the multiset is a fraction of type 1 divided by 2 at power I. Among those examples, we can call 1, 1 divided by 2, 1 divided by 4, 1 divided by 8, and so on. Since the answer may be large, we need to print in modulo this huge number. And the constraints are not very big, but still not small enough to allow weaker solutions or brute force approaches to pass. Since we have these kind of numbers which have a special form, we may think two approaches. The first approach would be to try and find some math solution, maybe using some formula, maybe by some other way. And the second approach would be the DP1. And when I solve this problem, since I'm better at DP than I am at math, I decided to go with the DP solution. And at first, I found a weaker DP, which runs in like n to the third. And that wouldn't be fast enough because the time limit is 2 seconds. But I decided to use that DP and see if it's correct in order to maybe find some other observations, which will lead me hopefully to the fast enough solution. Now I'm going to explain both DPs, both my first DP, which is weaker, and then the second DP, which is the actual solution. Now, in order to explain the first DP solution, I have to also say the following observation. Since n and k are both up to 3000, this means that every number of form 1 divided by 2 at x, where x is bigger than 12, I think, can be used in any solution. Because 2 at 12 is 4096. And if we add up 3000 numbers of this type, we would get something like this, which is smaller than 1. So we can't actually use them in order to solve this problem. So we are left with a few fractions. And this leads us to the following observation. Why shouldn't we recompute some DP in order to solve the remaining part of the task using a knapsack? And the knapsack would be quite easy to use. And that's what I initially did. In the first DP, I pre-computed a recurrence like this. So that would be DP of I and j, which is the number of ways we end up with a sum equal to 1 divided by 2 at I if we use j numbers. And the reason why I pre-computed this is because in the end, it would lead me to several numbers like dp of 0 and j, where j would be up to 3000. And from that point on, I would be able to make knapsack. In order to pre-compute this, I used only fractions which are either smaller than this one, or that fraction which is equal to 1 divided by 2 at I. So the recurrence would be something like we are going to get the values for this state from the states of type like dp of x, which is bigger than I, and j minus ix, which would be a number of fractions we would have to add up in order to get to our fraction. But the problem with the solution was that its complexity would be n at the third, and that wouldn't be fast enough for our problem, since we have n and k up to 3000, and the time limit would be 2 seconds, and the number of operations done would be too big for this to work as intended. But the good thing about this DP is that it led me to the following observation. Why shouldn't we care about whether we add a 1 or some fraction? Maybe that would make it easier. And so it happened. Now, again, let's assume that, like in the previous DP, namely in the knapsack part, we are at a state ij, which is the number of ways to use I numbers such that their sum is j. And obviously, in the end, we would have to get to a state nk, according to the problem statement. Now, how can we get to ij? There are actually two options, as I said earlier. Either we are going to use a 1, so we would have to take from I minus 1, j minus 1, or we can assume that we are using smaller fractions, and by assuming that, we can literally multiply all the fractions used by 2 in some other configuration, and we would take numbers from I and j times 2. It is equivalent. If you write some smaller fractions and then multiply by 2, it's the same thing, because the fractions respect a geometrical progression, and we are allowed to do this. Now, in order to implement the solution, we only have to create a simple 2D array and some simple implementation, as I'm going to show right now. As you can see here, I have quite a small code, which is usual for the AtCoder tasks. And here I'm initializing the DP solution with DP of 0, 0, which is 1. Namely, the number of ways to get an empty set with a sum equal to 0 is 1. And this will be the starting point of our solution. Now, for all the states ij, such that j is not bigger than I, we will use the recurrence I described earlier. And namely, we will add up dp of I minus 1 and j minus 1. This means that we are going to add on 1. Or if j plus j is not bigger than n, the number of elements we can choose, then we are going to add up also dp of I and j plus j, which is based on the fact that we multiply those fractions by 2. And now at the end, we are going to print dp of n and k, which is the answer required by the problem. One should be careful also at the mode, even though the time limit here is good enough so that I wouldn't have to add additional if statements for the modding. In some cases, it may be a good practice to firstly do the addition and then checking if dp of I and j is bigger or equal to the mod, because mod is not the fastest operation. And you have already seen this in my previous videos and also maybe in practice. If you liked watching this video, please like the video, subscribe to the channel, and press the bell button in order to get access to all the notifications and to the videos as soon as they are published. You can also check out my other links in the description. And until the next time, stay safe, stay healthy, good luck, and goodbye.